Good morning, dear students. So, last time we were discussing about the 5 steps of extraction of metal. So, what was number 1 step? Step number 1? Step number 1 was crossing and grinding. Crossing and grinding. So, in that crossing and grinding, we were just making this used rocks into powder so that the surface area increases and this one and the concentration of ore can be done very easily. So number 2 is concentration of ore, and concentration of ore can be done in 4 ways. Number 1 is gravity separation. Generally gravity separation is done on the basis of density difference, and number 2 is magnetic separation. So in this magnetic separation, generally one either ore or impurity has to be magnetic. If ore is magnetic, then impurity has to be non-magnetic. If ore is non-magnetic, then impurity has to be magnetic. Then comes froth flotation. So in this froth flotation, one has to be hydrophilic and one has to be hydrophobic. Either one. Okay, generally in this case ore has to be lighter, and ore has to be hydrophobic. That means it should repel from water. And last one is chemical method, that is leaching, and here what we do is one has to be soluble. Generally ore has to be soluble and impurity has to be insoluble in a particular reagent. So these are 2 steps that last time we discussed. Now today we will be discussing step number 3. Step number 3. So what is step number 3? Oxidation of ore. What we do here? Oxidation of ore. So what is oxidation of ore? Generally it is conversion of ore to metal oxide. Conversion of ore to metal oxide. Conversion of ore to metal oxide. So why we convert ore to metal oxide? It is because to extract metal, our main intention is to extract metal, to get metal from ore. So for doing so, for doing this, for extracting metal, it will be easy for us to do it using metal oxide. That's why we convert ore to metal oxide. Now this can be done in 2 ways. One is roasting and the other is calcination. So these are 2 processes for conversion of ore to metal oxide. Conversion of ore to metal oxide can be done in 2 ways, roasting and calcination. Now, what is roasting? Roasting is the process of converting ore to metal oxide in presence of oxygen. That means in presence of air. That means there has to be huge supply of air. Heating in presence of oxygen or air is roasting. Here, presence of oxygen or air. That means it is heating. This is heating in presence of oxygen or air. That means here what we do, we heat the ore in presence of oxygen And in calcination, what is calcination? The process of converting concentrated ore that we get in step 2. Concentrated ore. So this concentrated ore that we got in step 2 is to be converted to metal oxide, and this can be done in two ways, that is roasting and calcination. So how do we do roasting? In roasting, what we do? We heat the ore in presence of oxygen, and in calcination, heating of ore in absence of oxygen or air. So here, presence of oxygen or air, and calcination, absence of oxygen or air. Okay, now let's see now which of the ores we do. Which of the ores we convert to metal oxide by using which of the process? Let's see. This roasting is generally used to convert sulfide ore to its oxide. Sulfide ore to oxide. That means roasting can be used to convert sulfide ore to oxide, and calcination is used to convert carbonate ores to metal oxide. That means by using the process called calcination, we convert carbonate ores to metal oxide. By using roasting, we convert sulfide ore to metal oxide. For example, zinc sulfide. Zinc sulfide is ore for metal zinc. Okay, zinc sulfide is the ore for the metal zinc, and ZnS is also called galena. So ZnS in the supply of oxygen, and this has to be heated above 300 degrees Celsius. Okay, this is to be heated in presence of oxygen. Then what we get? We get zinc oxide plus sulfur dioxide. Zinc oxide plus sulfur dioxide. Let's balance zinc 1, sulfur 1, and sulfur 1, oxygen 2 and oxygen 3. So balance this. 2 ZnO, Zn2, then S is 2 now. So this also you make 2, S2, and 2 2s are 4, 2, 6. So balance. So zinc sulfide is the ore which can be converted to zinc oxide by using the process called roasting in presence of oxygen, heating in presence of oxygen. Okay. Then this one, for example, calcium carbonate. Now calcium carbonate, here zinc sulfide has no oxygen in the ore, but calcium carbonate has oxygen in the ore. So basically you don't have to mug, you have to understand. Basically what happens here? Here is the presence of oxygen, so we need no extra oxygen. That means it can be heated in absence of oxygen. But sulfide ores, they do not have oxygen in their molecules, so they need oxygen. This is one of the trick to know which ore we convert to metal oxide using which of the process. So calcium carbonate and heating in absence of air, in absence of oxygen, to give calcium oxide plus carbon dioxide. So this is metal oxide. We are getting, this is ore and this is metal oxide. This is ore and metal oxide. This is ore, and this is metal oxide. Okay. Now I will tell you one trick. See, roasting as sulfide ore, that means roasting is used for sulfide ore, and calcination Ca, carbonate Ca, carbonate Ca means calcination carbonate. Okay, so calcination for carbonate ores, and there is no S in this word, but here S. So roasting for sulfide ore, roasting for sulfide ore. Okay, so first step is crossing and grinding, second is concentration of ore, then third is oxidation of ore, and oxidation of ore for what we do, conversion of ore to metal oxide, and this can be done in two ways, roasting and calcination. Roasting in presence of oxygen, calcination in absence of oxygen. Roasting is done for sulfide ore, calcination is done for carbonate ores. Now what are some of the similarities? What are some of the similarities of roasting and calcination? Both of these process is used to remove moisture. That means both processes are used for converting ores to oxides. Ores to oxides. Okay, both are the process of converting. Both process are used for converting ores to oxides. Number two, in both the process, moisture is removed. Moisture is removed in both the process. Okay, in roasting also moisture is removed on heating, and in calcination also moisture is removed on heating. Then organic matter, whatever organic matter is there in the ore, organic matter that is there in the ore is also removed. Organic matter is removed. Organic matter is removed. Then both the process makes the ore porous. Makes the ores porous. Makes the ores porous. And heated uniformly. So if they are porous, then they will be heated uniformly. They will be heated uniformly, because this process makes the ores porous. So they will be heated uniformly. Okay, so these are some of the similarities. And what are the differences between roasting and calcination? Roasting is done in presence of air or oxygen. Calcination is done in absence of air. Roasting is done for sulfide ores. Calcination is done for carbonate ores. That is the difference. These are the similarities. That is the difference. Okay, that's it for this one. For oxidation of ore, so we are done with the step number 3. Now we will be doing step number 4. So what is step number 4? What is step number 4? Step number 1 is crossing and grinding. Step number 2 is concentration of ore. And concentration of ore can be done in 4 ways. They are gravity separation, magnetic separation, then flotation, and chemical method, that is leaching. Then step number 3 is oxidation of ore, and that can be done in 2 ways, that is roasting and calcination. Roasting in presence of air and is used for sulfide ores. Calcination is in absence of air, and that is done for carbonate ores. Now we will be doing step number 4, that is reduction of metal oxide to metal. Reduction of metal oxide to metal. Reduction. Okay, reduction. That means, what is reduction? Removal of oxygen. What is reduction? It is the process in which oxygen is removed by using reducing agent, or removal of oxygen takes place in any ways, that is reduction. So how do we get metal? Our intention is to get metal. Our intention is to get metal, not only metal, pure metal. So how can we get metal? By reducing metal oxide. That means by removing oxygen from metal oxide. Okay. So this reduction of metal oxide to metal is there for different metals. Different metals will be using different reducing agent. And generally for these we'll be following this one, reactivity series. Reactivity series. So in reactivity series, first one is potassium, then sodium, then calcium, then magnesium, then aluminium, then comes this one, zinc, then iron, then lead, then copper, then mercury, then silver, then gold, then platinum. So it goes like this. Now from potassium to aluminium, they have different ways of reduction. Then zinc has different ways, then this one, lead, iron, copper has a different way. Okay, so let's see now step wise. Okay, see here, copper oxide. Okay, copper oxide, it has oxygen, so it is oxide. So copper oxide, how can we reduce copper oxide to copper? So copper oxide can be reduced to copper by using carbon, which is also called coke. Pure carbon, which is also called coke, solid form of carbon. Okay, this is pure coke, carbon. Okay, so this pure carbon has strong affinity towards oxygen, strong affinity, or you can say strong attraction towards oxygen. That means this has the tendency to attract oxygen towards itself. That means it has a strong affinity towards oxygen. It has the capacity to add oxygen in it. So this carbon, when comes in contact with copper oxide, then this oxygen comes and get added to carbon. So what we get then? Cu plus Co. That means Cu, metal. Here this is metal oxide, and this is metal. That means metal oxide to metal. So reduction is taking place. And this can be done by heating. So here carbon is reducing agent. Copper oxide is converted to copper. And for this process, what is helping? Which substance is helping? This carbon is helping. So carbon is reducing agent here. So carbon is getting oxidized and copper oxide is getting reduced. Okay. Now again, this copper oxide can be reduced to copper by taking carbon monoxide also. So carbon monoxide is also a good reducing agent. It also has strong affinity towards oxygen. That means it also has tendency to get added with oxygen. It also has the tendency to attract oxygen. So carbon dioxide on heating gives copper plus carbon dioxide. So carbon monoxide on heating with copper oxide can give copper plus carbon dioxide. Then again, copper oxide can also be reduced by using hydrogen. So in this case, what we'll get? We'll get copper and this hydrogen and oxygen. Here oxygen and carbon monoxide. Here's carbon and oxygen. So H2 plus O, we get H2O. H2O. So in this way, copper oxide can be reduced to copper metal. Metal oxide to metal. Okay? And here, carbon monoxide, hydrogen are reducing agents. Reducing agents. Reducing agents. So these oxides, copper oxide, okay, can be reduced to copper by using carbon monoxide and hydrogen. Now, similarly, we can reduce iron oxide and lead oxide into metal by using all these three reducing agents. So in place of copper oxide, we can take lead oxide, then we will be getting metal lead. Here if we take lead oxide, we will be getting lead plus carbon dioxide. Here also lead plus water. Similarly, iron also can be reduced in this way. Iron also can be reduced in this way. Iron FeO plus C gives Fe plus CO. FeO plus CO gives Fe plus CO2. FeO, iron oxide, 2. Here also we can get iron plus water. So that means by using carbon monoxide and hydrogen as reducing agent, which of the metal oxides can be reduced? Using carbon monoxide, hydrogen as reducing agents, iron oxide, copper oxide and lead oxide can be reduced to metal, can be reduced to respective metal, can be reduced to respective metals. Okay. So these three reducing agents can be used for three metal oxides. Okay. That means iron, lead and copper. Now, if you come little up, that means above iron, okay, then we get zinc in reactivity series, we get zinc. Now, zinc, if we take zinc, then if we take zinc oxide, so what do you think? Zinc oxide can be reduced by using all these three? No. Zinc oxide can be reduced by using carbon only. Okay? Zinc oxide can be reduced by using carbon only. And what will get? Zinc plus carbon monoxide. This is metal oxide and this is metal. So zinc can only be reduced, zinc oxide can only be reduced by using carbon. by using carbon. Carbon monoxide and hydrogen cannot be used for reducing zinc oxide to zinc. Are you clear? For zinc oxide, we cannot use carbon monoxide and hydrogen because this zinc oxide is somewhat stable. So, carbon monoxide and hydrogen cannot break this oxide into metal. But carbon can break. Carbon, that means among carbon monoxide and hydrogen, which has the strongest affinity towards oxygen, carbon, coke, has the strongest affinity towards oxygen. That's why this carbon can only take oxygen from zinc. Carbon monoxide and hydrogen cannot. Okay? So zinc can only be reduced. Zinc oxide can only be reduced to metal zinc by using carbon as reducing agent. Okay. Now this is done. Then silver oxide and mercury oxide. Silver oxide and mercury oxide. So silver oxide and mercury oxide are very unstable oxides. So these are very unstable oxides. Okay, these are very unstable oxides. Their oxides are very unstable, not stable. That means it is easy to break the oxide into metal. It is very easy to break the oxide into metal. So simply by heating these oxides, we can get metal. Simply by heating. That means we need no reducing agent. We need no reducing agent for converting silver oxide and mercury oxide to respective metals. No need of reducing agent. By heating these oxides, we can, by heating these oxides, metal can be obtained. So silver oxide Ag2O on heating, Ag2O on heating, but heating should be above 300 degrees Celsius. If you heat this silver oxide, this is silver oxide. If you heat this silver oxide above 300 degrees Celsius, then you'll be getting silver plus oxygen. So why this is breaking so easily? Because this oxide is very unstable oxide. So by simply heating above 300 degrees Celsius, we can get silver plus oxygen. So balance this. Okay. Similarly, mercury oxide and GO. Mercury oxide also can be heated above 300 degrees Celsius to get mercury plus oxygen. So this way we can get metal from metal oxide by heating only. And which of the metal oxides can be reduced to metal by simply heating it? They are silver oxide and mercury oxide. And which of the metal will go for the most reactive? Metal oxides. And which are the most reactive metal oxides? Which are the most reactive metal oxides? Oxides of metal which lie on top of the metal reactivity series. That means oxides of potassium, sodium, calcium, magnesium, aluminium. Metal reactivity series goes like this: sodium, potassium, calcium, magnesium, aluminium. These are some of the most reactive metals. And their oxides are very stable. They form very stable metal oxides. They form very stable metal oxides. So these metal oxides cannot be broken to metal. These metal oxides cannot be reduced to metal by using reducing agents. So metal oxides, very stable metal oxides, cannot be reduced by using reducing agents. Okay? Then how to get metal from these metal oxides? Simply bypassing electricity through these metal oxides. We can get metal, and the process is called electrolysis, or we can say electrometallurgy also. So what is electrometallurgy? Electrometallurgy is the process of extracting metal from oxides by using the process called electrolysis. Now what is electrolysis? Electrolysis is the process of breaking a compound into respective elements by passing electricity through heat. So in that, what we do is we take a voltmeter. This is a voltmeter. Okay, that means the container in which we do electrolysis, and then we take used metal rods. Okay, metal plates, and these are called electrodes. One is connected to positive side of the battery, and one is connected to the negative side of the battery. So this is connected to positive side, so this becomes anode, and negative cathode. So positive and negative. So these are electrodes, this voltmeter, and through this battery electricity is produced, and here is the solution of metal oxide. For example, here is the solution of potassium oxide. Then what happens? Then potassium oxide on applying electricity breaks into potassium plus oxygen. Now this positively charged potassium moves towards cathode or anode? Positive charge. Unlike charges attract each other, means this moves towards cathode, and oxygen moves towards anode. Cation to cathode, anion to anode. Cation moves towards cathode, anion moves towards anode. So in this way, this potassium gets collected in cathode. And oxygen gets collected in anode. So in this way, we can reduce very stable metal oxides to metal. That means very stable metal oxides can be reduced to metal by using the process called electrolysis. Okay. So, this way, very stable metal oxides of sodium, potassium, that means from sodium to aluminum oxides can be reduced to their respective metals by using the process called electrolysis, and in metallurgical term we say it is electrometallurgy. Electrometallurgy. Okay, so simply in short, if I have to write, then very stable metal oxides can be converted to metal by using the process called electrolysis. So this is only the way through which very stable metal oxides can be converted to metal. There is no reducing agent which can reduce these metals to respective metals, metallic oxides to respective metals. Okay, so by this we have come to the end of step number 4. Let me repeat it again. Step number 1 is crossing and grinding. 2, concentration of ore. 3, that is oxidation of ore or conversion of ore to metal oxides can be done in 2 ways, roasting and calcination. And 4, that is reduction of metal oxide to metal. So reduction of metal oxide to metal can be done in many ways by using reducing agent like this one, carbon monoxide, hydrogen and ammonia, copper oxide, iron oxide and lead oxide can be reduced to metal, and zinc oxide can only be reduced by using carbon. Then silver oxide and mercury oxide are very unstable oxides, so can be heated to get respective metal. And then very stable metal oxides from potassium oxide to aluminum oxide can be reduced to metal by using the process called electrolysis. And in electrolysis we do electrolysis in this way by passing electricity. A cation metal ion moves towards anode, okay, and anion moves towards anode, cation moves towards cathode. That means we can get metal, pure metal in cathode. We can get pure metal in cathode. Now, the last step is refining. So why we do refining? Why to do refining? And how do we do refining? Refining. Number 5 is refining metal to pure metal. So our intention, our aim is to get pure metal, is to get 99% pure metal. Okay, so whatever metal we are getting by using this reducing agent and all, they may not be 100% or 99% pure. Okay, the copper that we get in step 4, the zinc that we get in step 4, the lead we get in step 4 may not be that much pure. So refining is the process of converting metal that is extracted in step number 4 to pure metal, 99% pure metal that can be used is refining. So in this refining, what we do is we purify metal. So this refining can be done in many ways. Refining can be done in many ways for all the metals. For example, liquefaction, distillation, electro refining, and many other processes are also there. But in your syllabus, what is there? Only electro refining. So we'll be talking about electro refining. We'll be talking about electro refining. So what is electro refining? Electro refining is the process of refining metal, impure metal, to pure metal by using the process called electrolysis. So electro refining is the process of converting impure metal to pure metal by using electricity or by using the process called electrolysis. So this is electro refining. So how do we do this electro refining? Let's see. First of all, take a voltmeter where we can perform electrolysis. Okay, and in this voltmeter you take a solution. Take a solution. Okay, take a solution, and with solution, what kind of solution we take? This solution is called electrolyte. This solution is called electrolyte. Solution is called electrolyte. Okay, this solution is called electrolyte, and this solution has to be of the metal. This solution has to be of the metal. Generally, solution has to be of salt, and this salt has to be should be of the metal to be purified. So salt or electrolyte, solution means this solution is electrolyte, and this electrolyte has to be salt of the metal to be purified. The metal which we are going to purify, okay, the metal which we are going to purify should be taken as the salt of that particular metal should be taken as the electrolyte. And then in this we take a used metal plate. Used metal plate. Two metal plates will be taken. Two metal plates will be taken. Okay. Two metal plates will be taken. Then this is a battery. This is a battery. Now you can see this is positive of the battery, positive. This is battery, negative of the battery. So positive of the battery and negative end of the battery. This positive end, the plate which is connected to the positive terminal of the battery will have positive charge, and this is called anode. So what is anode? Anode is the electrode. Anode is the electrode. And first of all, let me define what is electrode. Electrodes are the metal plates or metal rods which allow electricity to pass through the solution. Okay, which allows electricity to pass through the solution and leaves the solution are called electrodes. And these electrodes are of two types. They are cathodes and anodes. Anodes are positively charged electrodes. Cathodes are negatively charged electrodes. So anodes are positively charged electrodes, and this is cathode. Cathodes are negatively charged electrodes. Cathodes are negatively charged electrodes. Anodes are positively charged electrodes. Now, this anode, we take the anode of impure metal. We take anode of impure metal. That means the metal which we got in step 4, the metal which we got in step 4 has to be taken as anode. So which has to be anode? Impure metal has to be anode. And in cathode, we take pure metal. pure metal. We take pure metal. Example. Say for example, I'm taking copper. Okay. So copper extracted in step number 4 is used as impure copper. Okay, impure copper. Example, impure copper. Impure copper as anode. Then pure copper has to be cathode. Pure copper. Pure copper, which is already refined. Okay, which is already refined. Pure copper has to be used as cathode, and cathode generally has to be very thin. Anode has to be thick. Cathode has to be thin. Now, what happens is, I'm using impure copper as anode and pure copper as cathode. Then the solution or electrolyte also should be of copper. So I'm taking now electrolyte salt, that is copper sulfate solution. So what is the electrolyte? I'm using copper sulfate solution as electrolyte. That means anode impure copper, cathode pure copper, and solution copper sulfate solution. If I have to refine silver, then impure silver in anode, pure silver in cathode, and this has to be either silver chloride, silver sulfate, the salt of silver. If I have to purify iron, then impure iron here as anode, pure iron as cathode, and salt of iron, either iron sulfate, iron chloride, any. Got it? So what has to be there? Anode has to be impure metal, cathode has to be pure metal of the same metal, pure metal of the same type, same kind, same. Then salt has to be of the same metal. As electrolyte. So this is the arrangement of electrolysis. This is also called the process. This process is called electrolysis, and since we are purifying the metal here, so this is electro refining. We are refining the metal, so this is electro refining. But generally this comes under electrolysis. Okay. Now see here, I'll give you some short tricks, some short ways. PAO. So full form for PAO will be positive anode. So PAO, positive anode oxidation. Anode has to be positively charged, and in this particular electrode, oxidation takes place. So this is short PAO, positive anode. That means you will not have any doubt. Anode has to be positive. And in anode what happens? Oxidation. Oxidation takes place in anode. Now see here what happens in anode during this refining, during the electrolysis. So what happens? Generally here, say for example, we are going for copper. So what happens is when this is connected, then electricity flows like this. Electricity flows like this. This is the flow of electricity. Okay, this is the flow of electricity, but flow of electron will be just opposite. If electricity is moving like this, then electron moves like this. Okay. If electricity is flowing like this, then this is flow of current. But this is flow of electrons. So if current is flowing like this, then electron flows like this. Electron flows like this. Electron flows like this. This is the flow of electron. They are just anti-clockwise. If one is clockwise, if flow of current is clockwise, then flow of electron is anti-clockwise. In detail regarding electrolysis will be doing in the chapter called electrolysis. So what happens here then? We see this is anode. Electricity is coming like this. Electricity is coming like this. So what happens is we have taken here the impure metal. What is here? Impure metal. So this impure metal is copper Cu. This is impure metal. Impure copper. Impure copper Cu. This Cu on passing electricity. Cu on passing electricity, this is what happening at anode. What is happening at anode? On passing electricity, copper loses 2 electrons. On passing electricity, this copper, that means impure copper, loses 2 electrons and becomes Cu2 plus. That means this is becoming cation and losing 2 electrons. Now that means here is loss of electrons and loss or removal of electron. Then removal of electron is called oxidation. So oxidation. Loss of electron is called oxidation. So electrons, this is loss of electron takes place. So oxidation, loss of electron. So oxidation. So Cu2 plus. Okay, that means this impure metal gives Cu2 plus. And then this Cu2 plus comes to the solution. Okay, this Cu2 plus comes to the solution. Now in solution on passing electricity, what will happen? Copper sulfate solution is there. This copper sulfate on passing electricity breaks into Cu2 plus SO4 2 minus. So this copper sulfate breaks like this. This is cation and this is anion. This is cation, this is anion. Got it? So cation moves towards cation. That means what is happening in the solution? This is breaking like this. Copper sulfate is breaking like copper and sulfate ion. And cation moves towards cathode. This Cu2 plus moves toward negatively charged cathode. And SO4 2 minus moves towards anode. Then this Cu2 plus is moving towards cathode, and sulfate ion is moving towards anode. And from this anode, what is there? Cu2 plus is there. So this sulfate ion again combines with copper ion and makes copper sulfate. Again, that means it takes place. Again, copper from solution goes to cathode and copper from anode comes to the solution, combines with sulfate and again forms the solution. In this way, what happens is solution will not finish. Solution will remain as it is until and unless copper is supplied from anode. Until and unless copper is supplied from anode, copper is not getting short in solution. That means solution will remain as it is until and unless copper is supplied from anode. And copper from the solution will go to cathode. Will go to cathode. Now what happens in cathode? Let's see. Cathode can be written as NCr. NCr. Okay? Or I will write separately here. NCr. NCr. N means negative. Negative. C means cathode. And R means reduction. 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 So negative cathode reduction, positive anode oxidation. Anode is positive and oxidation takes place in anode. Cathode is negative and reduction takes place. So what happened in cathode now? What happened in cathode? This Cu2 plus is moving towards cathode. So Cu2 plus is coming to cathode. That means at cathode. What happens at cathode? What happens at cathode? Copper ion is coming towards cathode, and these two electrons from anode, moves to cathode. These two electrons from anode moves to cathode. So Cu2 plus 2 electrons. That means copper ion moves towards cathode and gains 2 electrons from cathode, which has come from anode. Cathodes are electron rich plate and anodes are electron deficient plate. So 2 electrons comes to cathode and Cu2 plus moves towards cathode and receives 2 electrons and forms Cu. That means here we'll be getting pure metal. So impure metal was there, impure copper was there in anode, and we are getting pure metal in cathode. So this way with the time passing, okay, as the time passes, this anode will be deteriorating. This anode will become thin and thin. And this cathode will go on increasing the size. It will become thicker and thicker. So why it is happening? Because all the copper from anode goes to the solution, and from solution copper goes to cathode. So cathode becomes thicker and thicker, and anode becomes thinner and thinner, and finally when whole of the copper from anode is finished, when whole of the copper is finished from the anode, then the electrolysis stops. Then what will happen? Whatever impurity is left, this impurity settles down. This impurity settles down. And this is also called malt. Then refining finishes. This is the end of refining. So what will happen here? Cu2 plus 2 electron. That means here we are gaining electron. There is gain of electrons. So in cathode, gain of electrons takes place. So it is reduction. And in anode, loss of electrons takes place. So it is oxidation. So this is refining. Now, cathode, finally at cathode will be getting pure metal, and anode will deteriorate because whole of the copper comes to the solution, and whatever impurity is left will settle down in the form of malt. This way we can get pure metal. So this is end of all the steps of extraction. So how many steps are there? First of all, what we'll do, we'll go for the this one, a site of ore. Okay, then we'll go for extraction of the ore. Then we start this one, crossing and grinding of the ore, where used rocks are converted to the fine powders. Then we do concentration of ore, that means separation of impurities physically, which can be done in very simple way by using hand picking. Otherwise, we can use other 4 steps for different types of ores. Gravity separation, which depends on the difference between the densities in impurities and ores. Then we go for magnetic separation for magnetic and non-magnetic ores and impurities. Then we go for froth flotation. If generally froth flotation is done for sulfide ores. Here ores has to be lighter than the impurities. Ores comes in the form of froth, and this one impurity settles down. Then some of the ores can be concentrated by using chemical method or leaching also, in which we use particular solvent, in which either ore has to be soluble and impurities has to be insoluble. This way also we can concentrate ore. Then we come for step number 3, that is conversion of ores to oxides, which can be done in 2 ways: roasting and calcination. Roasting for sulfide ores in presence of air, and calcination for carbonate ores in absence of air. Then after oxidation of ore, we go for reduction of oxides to metal. Okay, and in that also what we do, very less unstable, unstable oxides can be reduced by heating only. Mercury oxide and silver oxide are the very unstable oxides, which can be converted to metal by simply heating. And copper oxide, lead oxide and iron oxide can be reduced by using carbon in the form of coke, then carbon monoxide, hydrogen, ammonia. Then zinc oxide can be reduced to metal by using carbon only, because it has the strongest affinity towards oxygen. Other carbon monoxide and hydrogen cannot remove oxygen from zinc oxide, because zinc oxide is stable, somewhat stable you can say. Then very stable oxides can be reduced by the process called electrolysis. And then refining why we do, we get to get pure metal, we do refining, and refining can be done in this way. So anode we use impure metal, cathode we use pure metal. Then salt has to be of the same metal that we are using anode, that we are keeping anode. The metal that is to be refined, okay, the salt of same metal has to be taken as electrolyte. And then electricity is passed, then oxidation takes place in anode, then reduction takes place in cathode, and finally we get pure metal at cathode. So this way extraction of metal is done. Hope you will go through these, and this you can keep as the note also, you can write as the note also. Instead of going thoroughly through your book, you can make notes from this. Then you just do the works also. This much for today. Thank you.